We are going to continue to study the limiting behavior of a function as x approaches a, but in finer detail. You have probably seen graphs of functions that behave differently to the left of a than they do to the right of a, and more specifically, the limiting behavior of the function to the left and right of a. So it seems not all functions are as well behaved as to be nice and connected everywhere. We need to distinguish between the limiting behavior as we approach a from the left and approach a from the right. We see in the figure that as x approaches a from the left-hand side, the values of the function approach value L from below. And we can write, of course, instead of writing from the left, we can use more compact notation. We can place a minus in the superscript position for a to indicate that x is approaching a from the negative side of the number line. So next we're going to let x approach a from the right, and we see that the values of the function approach a value of r from above. We write that the limit as x approaches a of the function equals r from the right, and we'll use the shorthand notation by putting a plus as a superscript for a to indicate that we're approaching a from the positive side of the number line. So that's a quick review of the notation for one-sided limits. So here the limits from the left and the right don't agree. One place you may encounter the issue of the one-sided limits of a function not agreeing is with piecewise defined functions. The piecewise function is simply a function that's defined by different expressions depending on the value of x. So let's take a look at this contrived example where I stitched a bunch of expressions together on different intervals of x. For values of x strictly less than -2, the green expression defines the function. For values of x which are at least -2 but strictly less than 3, the blue expression defines the function. And for x's greater than or equal to 3, the orange expression defines the function. So for example, if we wanted to evaluate the function at -1, we would first check which interval -1 falls in. -1 is in the blue interval, so our function at -1 is defined by the blue expression. If I wanted to evaluate the function at x equals 3, you see that falls in the third orange case. So the orange expression defines our function at 3. Let's investigate the limiting behavior of a function as x approaches -2. We first attempt to compute the limit as x approaches -2 from the left. And because x is approaching -2 from the left, falls in the first green interval, where x is smaller than -2. So the first expression defines my function on that interval, and we can evaluate the limit directly to see that we get 0. Next, we want to consider the limit as we approach -2 from the right-hand side, or the positive side of the number line. So this time, even though x is very close to -2, it's slightly bigger than -2. So our x's fall in the blue interval. Our function is defined by the middle expression x plus 1, and we can evaluate the limit directly to see that the limit is -1. So we see that the two one-sided limits are not equal. As an exercise, if you need it, you can also check the limit as x approaches 3 from the left and the right, and you'll see that the limits do agree. Taking a quick look at the graph, we see that the function is disconnected at -2 because the limit from the left and the right don't agree. But the function is connected at x equals 3 because the limits from the right and left agree. Next, we're going to take a look at the function absolute value of x divided by x and rewrite it as a piecewise function. We're first going to review how the absolute value of x can be written as a piecewise function. Looking at the graph of the absolute value of x, if x is negative, then the absolute value of x is represented by the negative sloping line y equals -x. If x is positive, then the absolute value of x is given by the positive sloping line y equals x. So we can write that y is -x if x is negative, and y equals x when x is positive. Absolute value is also defined for x equals 0, so I'll just throw that case into the orange case. You can also reason that if you're taking the absolute value of a positive number, you can simply drop the absolute value, but taking the negative of a negative number leaves you with a positive number, so that has the same effect as taking the absolute value of that negative number. So let's now return to the absolute value of x divided by x. When x is negative, we replace the absolute value of x with -x. When x is positive, absolute value of x equals x. Simplifying the two expressions, we get -1 and 1. From a graph of that function, we see that the limit as x approaches 0 from the left is -1, and the limit as x approaches 0 from the right is +1. As a quick note, our function is not defined at 0. We could define a slightly altered function where it's equal to some constant, say 0, when x equals 0. Now, this wouldn't change the one-sided limits. Limits don't care what the function does at 0, only how the function behaves around 0. Okay, let's do this next example algebraically. We're going to compute the two one-sided limits as x approaches 1. Note that the absolute value of x minus 1 is going to be the negative of x minus 1 if x minus 1 happens to be negative. And when x minus 1 is not negative, we can simply drop the absolute value bars. Note that saying that x minus 1 is less than 0 is equivalent to saying that x is less than 1. And x minus 1 being at least 0 is equivalent to saying that x is at least 1. If you don't see it, just add 1 to both sides of the inequality. So now we're going to let x approach 1 from the left, and this means that x is less than 1. And so according to the definition of the absolute value of x minus 1, we can replace it with the negative of x minus 1. We can simplify and then evaluate directly to get 1 as our limit from the left. So next we let x approach 1 from the right, and we see that means that x is now greater than 1, so that the absolute value of x minus 1 becomes x minus 1. Doing some factoring and some cancellation, we get the limit as x approaches 1 of x plus 2, which we evaluate directly to get 3. The two one-sided limits, again, don't agree. Next, we're going to make some quick observations about the square root of x squared. This is a function, so given an input, it can only return exactly one output. And so what I'm about to write is wrong. I'm even a little nervous about writing it at all. The square root of x squared is not plus or minus x. And if we think about it, the square root of x squared should always return a non-negative quantity, because you square x, which gives you something non-negative, and you take the square root of that result, and square roots always return non-negative quantities. Consider -2 squared square rooted. Squaring the -2 gives you a +4. The square root of +4 is 2. So this function had the effect of taking the absolute value of -2. So now let's write down what square root of x squared actually reduces to. It's equivalent to the absolute value of x. When simplifying square root of x squared to the absolute value of x, we're simplifying an expression. That's different than solving an equation like x squared equals 4, where there could be many possible values for x that satisfy that equation. To solve for x in the equation, we can take the square root of both sides, and the left-hand side, square root of x squared, simplifies to the absolute value of x, so that x could be either plus or minus 2. We're going to use these ideas in the next limit problem. We're going to consider the function sine x divided by the square root of 1 plus cosine x. This function is not defined at x equals pi, because we get 1 plus cosine pi, or 0, in the denominator. So instead, we're going to look at the limiting behavior of the function as x approaches pi. Let me demonstrate how to do this problem incorrectly. I come up with a clever idea of multiplying by the square root of the conjugate of 1 plus cosine x on top and bottom. This algebraic trick introduces 1 minus cosine squared underneath the square root in the denominator. This gives me the square root of sine squared in the denominator via the Pythagorean trig identity. The square root gets rid of the squared in the denominator. We can then evaluate the limit of the simplified expression directly as x goes to pi, and we get square root of 2. Now, this result wouldn't give me full marks. The mistake I made is that the square root of sine squared of x is equal to the absolute value of sine of x. So let's revisit this problem and do it correctly. And this time we're going to compute the one-sided limits. We're going to let x approach pi from the left, and then we would again multiply by the conjugate in order to get a sine squared underneath the square root, but this time we correctly simplify the square root of sine squared to the absolute value of sine. Looking at a graph of sine of x, we see that as x approaches pi from the left, sine is positive. This means that the absolute value of sine is just sine. We cancel the signs and evaluate the limit directly to get square root of 2. Next, taking the limit as x approaches pi from the right, Nothing would have changed until that last step there where the absolute value of sine becomes minus sine. This is because as x approaches pi from the right, we see from the graph that sine is negative. After canceling the signs, we're still left with a factor of -1, and now we can evaluate directly, and this time the limit is negative square root of 2. The moral of the story is that the square root of box squared is the absolute value of box. If you don't know what's inside the box, go comments.